Good afternoon. I'll be discussing today a new subject. Not really new because we're talking about approximation methods, but we'll examine a third approximation method. We've covered two approximation methods. The first one is the strong form Galerkin. In the strong form Galerkin, you have the approximation function has to satisfy all the boundary conditions, essential and natural boundary conditions. Then we discuss the weak form Galerkin. In the weak form Galerkin, you only need to satisfy the essential boundary conditions. And in these two cases, you always start from the governing equation. In both of these cases, we start with the governing equation, and we form something called the weighted residual, right? And using the weighted residual in one method, the strong form Galerkin, we just take the residual function, make it orthogonal to the set of basis functions that form the approximation function, and then we are able to get, in that case, get n equations and unknowns. And as we found, with the strong form Galerkin, there are some difficulties. I have to satisfy all the boundary conditions, essential and natural, and also the order of differentiation is pretty high, is higher, right? And for us to be able to use an approximation method that's more suitable for finite elements, what we've done is we've weakened the continuity requirements by decreasing the order of differentiation using what method? Integration by parts. So we'll integrate by parts, and then we're able to weaken the continuity requirements. We will satisfy the natural boundary conditions implicitly in the weak form, and then we'll impose the essential boundary conditions on the approximation function. Hopefully that's very clear. Today we'll talk about functionals and another technique called Rayleigh-Ritz, which is also a third method that's using finite elements for approximating the behavior, physics behavior over a domain. This method, the Rayleigh-Ritz method, is a convenient method when you have a functional. There's a functional that describes the problem of interest. And these two methods are both used in finite elements. You can both use these methods in finite elements. A functional, what is a functional? A functional is a function of another function. Okay? So normally you will see that functions are functions of constants. You know, for example, fx equals x squared plus 3. That's a function because function here is a function of x. In the case of a function that's a function, what we're looking at is that, for example, in this scenario, we have I have a curve. I have some curve or a rope that I give you, and I tell you, hey, what is the shape of this rope that gives me the minimum distance between these 2 points? That's the question that I ask you. Anybody knows what's the shape of that curve that gives me the minimum distance? A straight line, right? And so if you were to write the equation for that differential length, you get ds equals square root of dx squared plus dy squared. You know, that's basically Pythagoras' theorem applied to this little strip. Okay? And so if I want to find the total length of that curve, I integrate this over from 0 to L, say, to this length here. I integrate this little differential across that curve. And so what I find is that the total length of the curve now is just basically this equation integrated over that domain. And if I divide everything by dx, then I can have an equation that just looks like this. Okay? Now you quickly realize here that this is a function, but that function, its value depends on another function. See, normally a function depends on x, or x squared, or x cubed. In this case, this function depends on another function. Okay? And in this case, the question is how to find this function that minimizes that function? That's a question that's being asked here. Okay. Now this is covered in a more advanced class called calculus of variations. And so I will not go into the extreme details of that, but I will explain to you how we can minimize this function that's a function of another function in a more direct way without getting into too much into calculus of variations. Is that clear what I'm talking about? How do I find the minimum on a function typically? I take the derivative of that function with respect to the variable x, the scalar quantity x, right? Say x is the coordinate system, coordinate value. Then I take the derivative of that function with respect to x, set it equal to 0, right? I cannot do the same thing here. I cannot take the derivative of L with respect to y and set it equal to 0. It will be incorrect because here, this function is a function of another function. So you have to approach it a little bit different. Let's look at the total potential energy. I'm going to talk about total potential energy. I want to show you an example of a functional. This is an example of a functional. So if I look at a 3D body, basically a total potential energy of a system, of a body, is essentially the strain energy stored in the body plus the work done by the external forces. That is the total energy, total potential energy. And so if I look at this total strain energy inside a body, let's call that U. Basically what I have is that U equals 1/2 the stress quantity in x direction times the strain quantity in x direction and so forth. And then I have the shear quantities that are also conjugate to the strain quantities in that direction. So this gives me a strain energy in the body, that's stored in the body, okay? And I cannot go too deep into the derivation where this comes from, but all I can tell you is that in the one-dimensional case, if I have the stress-strain curve, and I ask you, what is the strain energy per unit volume in the body, you will say, okay, it's the area under the curve. Well, yeah, that's 1/2 sigma xx times epsilon xx. That's what that is. And so if I integrate that over the volume, I get the total strain energy, for example, in a 1D elastic bar. So if I generalize this into a 3D case, you know, I basically have to add up the other terms that contribute to the total strain energy contribution, strain energy of the body. Okay. If I write this in matrix notation, I have the stress vector transpose times strain. That's exactly what this is here. Okay. And then we know that stress is related to strain through the constitutive relationship. So stress equals the constitutive relationship, Hooke's law, basically C times epsilon. So the stiffness matrix times the strain. And I gave you the formulas for C in the previous 2 weeks ago. And if I apply the transpose to this equation, this basically flips order, and I apply the transpose there. Now remember that the stiffness matrix is symmetric. Remember that? So therefore, C transpose is C. So in the 3D case, you can see very quickly now that the strain energy depends on functions. So this is a functional because this strain energy depends on these functions. These are functions, U, V, and W. These are functions that describe the displacement field. Okay? These are the displacement fields that we're talking about here. And so now if I look at the contribution of the work done by the external loads, I have 3 types of loads I could have in a body. And we talked about this a little bit at some point. You have tractions acting on the surface. I could have a point load acting at a particular point. In the body, I have a body force as an example. And so if I want to find out what is the work done due to these forces, I think you can guess, but it will be the force, basically the force times the displacement. Isn't that the work done, in essence? Force times displacement. So in this case, what I have is I have these body forces, and this is the vector of body forces. So these are the components here that you see here. So if I have a body force like gravity, right? Let's say it's a 1G load, you know, in the Z direction, so it's moving downwards. Then in that case, Bx is 0 and By is 0, and you only have Bz as an example. But the work done by the body force has to be multiplied by W, because that's the deflection downwards in this example, and that has to be integrated over the volume, because the body force acts over the whole volume. You agree? You agree that gravity acts on the whole body of the structure? So because of that, you have to integrate that quantity over the volume times that deflection, right? Times that deflection. And then I have traction forces acting on the surface of the body. On the surface of the body. In this case, and that's a mistake, that should be S, and I'll correct that. So we need to correct this page here. This will be surface right here. And the tractions are acting on the surface of the body, okay? And in this case, the traction multiplied by the deflection in that direction, plus the traction in the Y direction times the deflection in the V direction, plus the traction downwards or upwards, multiplied by the deflection in that direction. This over the surface, over this surface here, right here, that gives me the work done due to the traction forces, okay? And then for the point load, I will have, again, the load component is a vector, Px, Py, and Pz of that load vector. And each individual component multiplied by the deflection in that direction gives me the work done. Okay? For example, in this case, I have the load vector applied in this direction. Well, then you have a component of Py, in this direction, along the Y direction. So Py times the deflection of this point in this direction gives me the work done. That's an example. And so forth for all these guys, tractions and body force. Same concept, okay? So if I add up the strain energy stored in the body plus the work done by the external loads, this total amount is called the total potential energy. That's the total potential energy of the system, okay? And note, once again, that this total potential energy depends on three functions: U, V, and W, which are the deflections of the body under those loads. And you know that because strain, you tell me very quickly, does stress depend on strain? Yeah. Strain depends on deflection. Well, yeah, it depends on U, V, and W. So you can see quickly that all these guys depends on U, V, and W. And then, of course, that's very explicit here. You can see it. It depends on U, V, and W. So that's an example of functional. I'll give you an example of functional in a mathematical, form. Like, hey, I have a curve. What shape minimizes the shape of that curve? And then we know it's a straight line. But you saw in that example, that's a function of a function. And in a physics problem, this is a function of a function. Functional, okay? But there is a principle. And the principle is called the minimum potential energy principle. And this principle states that among all displacements that are possible in this structure, and what I mean with that, what I mean with possible, okay? So in this body, where is this body fixed? I'm going to fix it right here in this location, okay? Can I move the displacements here if it's fixed? No, they are what they are. So what the minimum principle of potential energy is saying is that the deflections in locations where they're admissible, the displacements are admissible, are permitted, while also satisfying those fixed boundary conditions, that the displacement field that corresponds to the one that minimizes the total potential energy, okay? And in that scenario, those displacements correspond to the system being in equilibrium. In other words, if I apply these loads to the structure will deform to a shape such that it minimizes the total potential energy and the body is also in equilibrium. You follow what I just said? I'll repeat it one more time. What we're saying here is that this principle is saying that when I apply loads to a structure, for displacements that are possible, that are admissible, those displacements will become those such that the system is in equilibrium and the potential energy has been minimized. Okay, I said it maybe 3 different ways. You saw that already. You applied that concept for the spring problem. We applied load to the spring. You calculate total potential energy, remember? 1/2 kd squared minus the load applied to the very end, right? And we minimized that function relative to the displacement. And what they give us? That gave us that the equilibrium of the spring. If you recall, we went through that exercise. So with that said, I could apply this concept to determine what are the governing equations? What are the equations that describe the deformations of the problems I have interest in? So looking here as an example, I do want to point out one more thing. The total potential energy can only be formed or described or well-defined for 2 very important requirements. The first one is that the deformation has to be elastic. So if I apply loads to structure and I remove the loads, the structure will come back to its undeformed shape. That's called elastic deformation. So you can write a well-defined total potential energy if that's the case. The second case is that when I apply loads, the loads are not follower forces. What I mean with that? So if in this case I have 2 beams, the beam in the deformed state, right, and the beam in the undeformed state. And if I apply a load in the x-axis in this direction, and the beam deforms, but it continues to act in that direction, doesn't matter what happens to a beam, you can see here that basically the load direction is not changing and the load is not depending upon the deformation. It's basically independent upon the deformation. In that case, that load is called conservative load. It means that it's not a follower force. In another scenario, you have the beam deformed here. You can see here that the load has switched angles because it wants to stay tangent to it. You can see that. In this case, the load does depend on the deflection. In that case, that's a follower force. So the total potential energy can only be well-defined when, and can be defined, in fact, when the deformation is elastic, number 1. Number 2, the load does not depend on the deflection of the beam. In other words, it's a conservative load. It only acts in one direction. Okay? Does that make sense, everybody? All right. So let's apply what we're learning, okay, to a 1D elastic bar. 1D elastic bar. In the 1D case, we don't have other stresses acting on this elastic bar, just the stress acting along the bar. And so for that reason, all the other 5 terms I had earlier, for example, I had like 6 terms right here, 1, 2, 3, 4, 5, 6. We'll just skip that one because we don't have these other strains acting on this elastic bar. We only have loads applied along the length of the bar. So if I look at the total potential energy for this 1D elastic bar, I have 1/2 the stress along the axis of the bar times the strain along the axis of the bar. And then I have the load applied on the top surface. I have a traction force acting on the top surface, which I've put Q bar times U dA. Okay, because the top surface has an area of the width, right, of course, times the length. And so this here represents the load, including it's basically units of traction, which is PSI. It's a pressure quantity. Okay, and then I have, and I'm just applying I'm just applying right now. What I've done right there is I'm applying this particular one here, the tractions. This should be S and S, so on the surface. So all I've done is substituted what the traction is, which is Q, because it's acting along the U direction. These ones are 0. I'm not applying tractions on the top surface that are in the Y direction or the Z direction, just along the U direction, where U direction is this way. Okay. And so then I have a load applied in either side. So then I have a potential work done, P times U. So that's minus P times U. And then I have a load applied here, P times U. So that's the work done due to, the work done because due to this one is that one. and the work done due to that one right on the other end is this one here. Okay, so that's the total potential energy for the 1D elastic bar in this example. Okay, everybody track so far? Okay, so if I continue looking at this, you guys know that stress equals modulus times strain, right? We talked about that, so I just substituted that here. So I get modulus times strain squared, in essence. And so for the rest of it, I haven't done anything else. The only thing I want to point out is that this Q bar, right, is per unit width also. So you can see the definition here. So what I'm going to do, I'll convert this Q bar into just Q and then integrate from 0 to L, right, so that we don't have to worry about the width direction, okay? Assuming that the elastic bar is of uniform width. That will just make it easier for us to carry out this operation. We also know that the strain, epsilon xx, is du dx. We showed you that formula. We showed you where that came from. So that's, and just to simplify, I just made a u prime squared. I just made it simple to see for us to operate on. Okay? So everybody agrees that this total potential energy looks correct for this bar. Yeah? Are we good? Okay, so what I'm going to do now, I'm interested in minimizing this total potential energy, which is a function. This is a function of another function, ux, and of course you can see here, there's a u here, a u there, a u there, a u there. Yeah, it is a function of a function. And I want to find what, so I am applying these loads to this structure. I want to find what displacements, right, minimize its total potential energy, because those displacements are the ones that render this system in equilibrium. That's what the principle of TPE is. Okay, total potential energy, TPE. That's what we're talking about here. You know, what displacements correspond to the minimization of this total potential energy, which also correspond to the governing equation that describes the system being in equilibrium. Okay. So how to do that? So to do that, we're going to talk about, you know, maybe you've taken an optimization course where you're looking for a line search, you're basically looking at a line search function, or you're looking at maybe you've taken numerical methods and you're applying a technique like a line search as well. This is very similar to that. You know, I can't really take derivatives of pi of this TPE respect to u directly. I cannot do that and set that equal to 0 to get the minimum, right? What we do instead is a Taylor series expansion. And I won't go into the details of that, but I'll give you the formula. You know, all you do is you try to minimize this function by looking at a direction v, arbitrary direction b, multiplied by a smaller scalar quantity, infinitesimal quantity epsilon. And so what we'll do is take the derivative of this respect to epsilon. Okay? So what we're really doing is, and this is called taking the directional derivative. You'll be doing this in your homework. Okay? You will take the directional derivative of the functional I gave you, and that gives you an approach to examining the neighborhood. You really, when you do a Taylor series expansion, all you're really doing is you're examining the neighborhood of that function and trying to understand in which direction this function is getting minimized. We're doing the same thing, but with functions of a function. We're trying to find in the neighborhood of that functional, hey, what function out there is going to minimize this functional? That's what we're really doing here. And so what we've done is added another function, but it's arbitrary, okay? And we're kind of saying, hey, what is, I'm going to add this amount, and hey, what direction gives me kind of like the right solution to this problem? That's what we're doing with this formula here. So all you have to do is plug in u plus epsilon v, v being an admissible, it's a possible function. You're going to plug that in into this formula, u plus epsilon v. Okay? So you plug it in here, and that's what I've done here. You will see I plugged it in, u plus epsilon v, u plus epsilon v. Everywhere where you see u, I replace it by u plus epsilon v. You can see that here very quickly. Does everybody track up to this point? Okay. This is actually a very advanced concept, and it takes me maybe a couple of weeks in a more advanced class, like some of you here know. So I am trying to give you enough so you know what we're talking about without not making a graduate level course. But it's still kind of graduate level, okay? I think you will get it if you follow. So here, initially we had u prime squared, and instead of u prime squared, what I've done is substitute that by u plus epsilon v, and then that's what you see. There's prime here and prime here. Epsilon is a scalar quantity. That's why you don't have to do anything with that. The next step is expand that out. So I'll expand that out, and you see that here. I expanded this out. So for the first term, I have u prime squared plus twice epsilon v prime u prime. That's what you see there. Plus epsilon squared v prime squared. So I've expanded everything there. I don't have to expand anything there. It's quite expanded very nicely. This one is expanded nicely. This is expanded nicely. Then when I expand everything, which is right here, I'll take the derivative with respect to epsilon of what I see here. That's what I'll do. Now I'll ask you a very quick question. Is u prime squared a function of epsilon? No. So when I take that derivative, that's going to go away. What is the derivative of this quantity with respect to epsilon? So what are you going to do? You're going to pretend everything else is a constant except for anything that shows up with epsilon. In this case, the only thing that shows up here with epsilon is this guy. Everything is like a constant to it. Relative to taking derivatives with respect to epsilon, everything looks like a constant. So what is that derivative of this quantity with respect to epsilon? 2, very good, 2u prime v prime, right? What is the derivative of this quantity with respect to epsilon? 2, very good, 2 epsilon v prime squared. So all we're doing is taking derivatives with respect to epsilon. If this, it doesn't have epsilon, it goes to 0, right? So this one, what is the derivative of u with respect to epsilon? 0. Okay. What is the derivative of epsilon v with respect to epsilon? V. Are you tracking? So we'll go one by one doing that, okay? And then at the very end, I'll evaluate the epsilon equals 0. Because that's what we're saying here in this formula. Substitute everything u plus epsilon v, take the derivative with respect to epsilon, and at the very end, evaluate that epsilon equals 0. All you're doing there is a Taylor series expansion. You're looking at second term of the Taylor series expansion, which tells you the stationarity conditions of that total potential energy.
Could you explain again why you set up equation u plus epsilon b?
Right. So your question is why I have made this u into u plus epsilon v. So what I'm doing here is a Taylor series expansion about epsilon, okay? And I'm searching for which function is the one that minimizes the total potential energy. So what I've done in essence is added a small quantity that is multiplied by an arbitrary function, that will help me determine that, okay? And then I can give you some more advanced lecture notes that can go into that, okay? So at the end we can talk a little more. But for the purpose of this course, this is what I'd like to discuss, okay? So now I'm going to go ahead and show you what the derivative looks like. So I took the derivative of that and I got this. We did it together. We did this together, remember? And now I will evaluate this at epsilon equals 0. When I do that, you can quickly see that this will go away, and that's about it. That's about it. Okay? Everything else stays put. Wow, I did that. I've added this epsilon equals 0. Does this look familiar to you? I'll give you 5 seconds and see if you remember this equation. Does that look familiar to anything we've done in lecture, Tuesday's lecture? That looks like the weak form. That's surprising. That looks like the weak form. Okay. Let's pretend for a second that did not happen. That's not the weak form. I think we're dreaming a little bit. But maybe it is a weak form. Let's revisit that. That was the equation for the bar. I multiplied by the weight function B. I integrated by parts. I got this equation here. It's starting to look familiar, doesn't it? And then I said, wow, this is the weak form. This is P basically. This is P in the other end. That's the weak form. I just got the weak form. So I minimize the total potential energy, and then what I got was a weak form. But the weak form came from this governing equation. So it's connected. The minimization of the total potential energy also implies this governing equation. It's the minimization of the total potential energy is connected through the weak form to the governing equation. They're all related. They're all connected, mathematically connected. So in other words, if I solve for the deflection in this governing equation, if I solve for the deflection in this governing equation, then I have found the displacement that minimizes the total potential energy. And I also have found that this is connected also through the weak form. Okay? So when I look at this diagram here, we minimize the total potential energy, and I got the weak form. I took the strong form, I weakened the continuity requirements, and I got the weak form. So they're all mathematically connected. Okay? So we'll revisit this again. I want you to think about that for a couple of minutes, because it needs to set in. I think it needs to set in a little bit. And I think while your brain absorbs what just happened, we'll do another example. Okay? Let's do another example. So let's take the beam, an example of a beam. In the beam, it's the same thing. We're going to ignore the other stresses because in a beam, the important contributor is stress along the length of the beam. Okay? So in that case, I have 1/2 sigma xx times epsilon xx. That's the strain energy for the beam. And the same thing, I have a transverse load. But in this case, the transverse load is not acting parallel to the bar. It's acting perpendicular to the bar. And if we call that W, the deflection W, then it should be Q times W. That is the work done due to that force, that traction force. Then I have point loads acting on the ends of this beam. Okay, there is a sign, a moment missing here, but there was a moment that should have shown up there. And so the work done, say for this load here, the one here at the end is Q3 times WL. The work done due to this load Q1 is Q1 times W at 0. Okay, that's that one. The moment, the work done due to the moment is moment Q4 times the slope at that location, W prime L, and similarly with the moment at the other end. So that was the potential energy. That is the potential energy of Euler-Bernoulli beam. Okay. Now, I will substitute, and you can go back to your notes to revisit this, but we proved that stress equals E times epsilon, so that makes it E times epsilon squared. And we also showed in the lecture, I believe number 2 or 3, that strain equals minus Y W double prime. We showed that. Go back and revisit that. It's basically the strain is the curvature of the beam. And as you see here, then I move on. Everything is basically the same. All I have done is here is instead of Q bar, which is acting on the top surface, I made it per unit width so that I can just integrate from 0 to L. Everything else stays the same. So let me continue operating on that bottom one. On the bottom one, I don't know if you notice there's a Y squared there. Y squared. And there's a dA. So I'll bring the Y squared out of there. And so I'll quickly realize here that integral of Y squared dA is basically inertia. Okay, I. Okay. This I should not be there, so the I should only appear after I made the operation, so I'll correct that. Minus integral of q w dx, and then I have the rest, okay? And so now the equation I get now is 1/2 EI w double prime dx qd, so forth, okay? That's the total potential energy of the beam. If I want to use the minimum theorem of total potential energy, TPE, what I need to do is basically find the minimum of this total potential energy. I have to find the minimization of that total potential energy. There's a small mistake, should be W, because it depends on the deflection W, okay? But it's a function. No, it's a functional because the function pi depends on another function, okay? And so, so if I minimize this total potential energy relative to that function W, then what I will find is the displacements are admissible that correspond to the minimum value of pi, but also represent the system being in equilibrium. So let's see how we will do that. So instead of W, I'll replace with W plus epsilon V. And then I'll take the derivative of that respect to epsilon and evaluate this at epsilon equals 0 and set that equal to 0. This is the method that you will use to determine basically what functions W make this functional minimum. That's how you will do it. Okay. In the example I gave earlier, which I did not finish, the example of the curve, and I ask you, hey, what is the curve that makes the distance between the 2 points a minimum? And the answer you gave me was a straight line. If you actually did this operation in that other problem, you will get a straight line. I mean, I didn't do it, but you can do it at home and you will see you get it. In fact, I'll give you 10 points extra credit if you go back to that. You know what? Those from 261A don't get that because I already did it for you. But the rest of you do get it, okay? If you want an extra credit, come at the end of the class and I have a special one for you, okay? Very special one for you. All right, so let me repeat the extra credit. If you were to find the minimum of this functional, and you prove to me that the function that minimizes this functional using the formula I just showed you is a straight line, then you'll get the extra credit, okay? That is what we're going to discuss here now. Application of this for the beam, how to do it for the beam. Okay, let me do it for the beam. For the beam, I'll do the same thing. I'll replace W by W plus epsilon V. And anytime I have W double prime, I just replace it in there, and you can see it there very nicely. Each of them, I just went through and substituted it. Same process. What is the derivative of W? Well, let me expand that. So I did expand that here. I expanded it so I can take the derivatives very carefully. Okay. At the bottom, I didn't have to expand anything. The only thing I expanded was this term here because it's squared. I expanded it, and then I took the derivative. So, for example, as an example, what is the derivative of W double prime squared with respect to epsilon? 0. I like how some of you just did that. That's correct. That's 0. What is the derivative of this with respect to epsilon? The same thing without the epsilon. What is the derivative of this with respect to epsilon? Well, it's twice epsilon V double prime squared. And I can continue on. So this is 0. That's 0. But remove the epsilon and so forth. So you can go on and do it. And at the end, I'm left with that. And I evaluate this at epsilon equals 0. And when I do that, this term goes away. And that's the only term that goes away. The 2 cancels out. And I get this. And again, that looks like the weak form for the beam, if you recall. In fact, it is the weak form of the beam. And it's, again, surprising, to some level. Well, it's not surprising because that's why it's called a principle, right? It's just telling you the principle actually does work. I'm just showing you it works, okay? And this is the weak form we got from weakening the continuity requirements from the governing equation of the beam. The governing equation of the beam was EI W4 primes minus Q equals 0. If I multiply by a weight function V, integrate that from 0 to L, and I weaken the continuity requirements and I form the weak form, I get the exact same thing that came out of the total, by minimizing the total potential energy. So you can see how all these things are connected. And once again, everything is connected. Strong form, from here I get the weak form. From here, minimizing this got me to the weak form. So in other words, if I solve for W here, that W is the one, in fact, is the one that minimizes this total potential energy. And this is how they're connected. Any questions on that? Any questions on that? So in both examples I provided you for the bar and the beam, it turns out that in a conservative deformation process, if you minimize the total potential energy, you get the weak form. And since the weak form, in the first place, was derived from the strong form, we got the weak form by deriving from the strong form. We got it from there. Then that tells you that the minimization of total potential energy, in fact, implies the strong form of the problem. They're connected. They're all connected. Therefore, if I were to approximate the solution to the partial differential equation, if I were to approximate the solution to this equation right here, in this case is an ordinary differential equation. If I were to solve this problem, this particular problem, then I'm basically minimizing this total potential energy. And so, if I approximate the solution to the PD using the weak form Galerkin, I can accomplish the same thing because since these two are connected, if I were to apply the weak form Galerkin here, and I get the approximate solution, I'm getting an approximate solution to this ordinary differential equation. But if I were to insert here an approximate solution in here, and then I minimize this function with respect to these unknown coefficients, what I'm really doing is approximate solution to the PD. They're all connected. It's connected. Okay? This method is called Rayleigh-Ritz. We'll take the approximate, we're going to assume approximate solution to the problem. We'll substitute it into the total potential energy. And then there, we will minimize the total potential energy. And if I do that, I can now find the coefficients that are known, and they turn out to be the values that correspond to the function that minimizes the total potential energy, which also correspond to the approximate solution of the ordinary differential equation. With that said, let's take a couple minutes break so I can let's take 5 minutes break so we can go into some examples. Now I'll continue with the Rayleigh-Ritz method. With the Rayleigh-Ritz method, like I said, we'll substitute an approximate solution of the partial differential equation, ordinary differential equation, into the total potential energy. You have a question, I'm sorry.
Yeah. What's the heat transfer analogy of total potential energy?
The question for the video here is, what is the analogy for the heat transfer problem, total potential energy? And the answer is in your homework. Look at your homework. The very first problem I gave you there is the analogy of total potential energy for heat transfer problem. And so you'll have great enjoyment because in that problem, you have to get the exact solution, which you can do very quickly in MATLAB. It's quadratic, actually. The solution is quadratic, polynomial. Then you'll do strong form Galerkin. Then you'll do the weak form Galerkin. Then you'll use Rayleigh-Ritz. Then you'll use Abaqus. And guess what? All 6 are going to match to like the 5th decimal place. Okay? I'm trying to instill confidence in you that this GUI that you're using is working. that this theory makes sense. That's what I'm trying to do. I'm trying to instill that confidence in you. Then the first problem has a second part. That second part is try to make you think a little bit. What's going on with the GUI? Okay. Second problem, I give you another differential equation, and I ask you to solve it two ways: strong form Galerkin, weak form Galerkin, and exact solution. I don't know if I do strong form Galerkin on that second problem, but you're going to have a good time. Okay, I think. All right. With that said, let's move to Rayleigh-Ritz. And so with this method, I think I've explained to you how that works. So for this example, let's take this approximate solution to the problem. Okay, I'll substitute this approximate solution to the problem into the total potential energy, and that's the total potential energy for this beam clamped with transverse loading. Okay, I'm giving you that information. If I plug this in here, which is shown here at the bottom, I want somebody to tell me, is that function of a function now? Can somebody tell me, is that a function of a function now? What is the only unknown in this total potential energy? The C's, this coefficient C's. These coefficient C's are scalar quantities. So now this functional, it got turned into function, a regular function. How do you minimize a regular function? You take the derivative of pi respect to the scalar quantity that you're trying to minimize it with respect to. So I take the derivative of pi respect to C1, set equal to 0. Respect to pi, C2, set equal to 0. That's all. That's all I have to do, because I've basically, what I've done is, I've chosen the form. I chose a space of functions. I've restricted the space of functions to one class of functions, so now I'm not looking for the function, how that function looks like. I already know how it looks like. All I need to know now is what coefficients I need to minimize that total potential energy. So in this particular problem, if I take the derivative of pi with respect to C1, derivative of pi with respect to C2, derivative of pi with respect to C3 up to Cn, I have n equations, n unknowns, and then I can find these coefficients. And guess what? These coefficients are the coefficients that when you plug it into your approximation function, which is this one right here, basically W equals that, right? If I know the C's, do I know W? Yeah. And that W, again, corresponds to the approximate solution to the differential equation, while also minimizing the total potential energy. They're all connected through the weak form. Let's walk you through an example very soon. So the approximate solution to the problem will give you a system of algebraic equations. And this is an approximate solution to the partial differential equation, and also is an approximate solution to the ordinary differential equation. And that approximate solution corresponds, in this particular problem, corresponds to the displacement field that minimizes the total potential energy while rendering the system in equilibrium when it's subject to those loads. Okay. The Rayleigh-Ritz approximation must follow the following guidelines. It's going to have to follow these guidelines. Each basis function you select must be continuous and differentiable. The approximation function is sufficiently differentiable and has to be sufficiently smooth. What do I mean with that? So if I go to my total potential energy, what order differentiation I have here? Second order. So if I choose a polynomial, what order can I plug in here at a minimum? Quadratic at a minimum. So this doesn't go to 0, right? The basis function must be complete and linearly independent. Finally, the approximation function has to satisfy the essential boundary conditions. Just that. That's all you have to satisfy. And each basis function must satisfy the homogeneous form of the essential boundary conditions, just like the weak form. Very, very similar to the weak form. Okay? Example 1. Example 1. take a clamp beam like the one I showed under distributed load. This was the total potential energy. This is the approximate solution. So that's the form that I'm going to select. And you can see very quickly here that this approximate solution satisfies the essential boundary conditions, because at W at 0, I get 0 and it's clamped on the left-hand side. That would make sense. If I take the derivative of this and I set that equal to 0, I also get 0. Works out is a clamped boundary condition on the left-hand side at x equals 0. If I plug in this approximation in here, look at how nice it looks. So pi now is a function of just C1 and C2. You see that? Yeah? C1 and C2. That's it. So then the derivative of pi with respect to C1 is 0. The derivative of pi with respect to C2 is 0. And then you get C1 and C2. You have two equations, two unknowns. C1 and C2 is the two unknowns. I have two equations. Solve for C1 and C2. I did a mathematical in a couple of steps. I put W, I did integrate, the function integrate. Then I did a solve with two two linear systems of equations. And I got the values of C1 and C2. I'll show you how to do it. If you want to follow, you can follow Mathematica. Okay. Let's take the example I gave in class last week, weak form Galerkin. For the weak form Galerkin, I want to show you how to get this approximation function, because I showed you that how to get this 5 or 6 different times. So not to be repetitive, you can go back and check. But this, I'm going to use the same form as what we got for that problem. Remember this problem, or you're forgetting? This is the problem we have. Plug it into your total potential energy, but now you have here, you have this P times the load. This is deflection here, right? I believe something got erased here, one step, so I'll put that step in there. But it's basically EI W double prime squared dx minus P times the load, the deflection at this end. So the deflection at this end is L, so put x equals L. So I get W naught plus C1 plus C2. That's what I get in there, right? And again, derivative of pi with respect to C1, derivative of pi with respect to C2, set that equal to 0, two equations, two unknowns. I did a Mathematica, couple of steps. Isn't that what I got with the weak form Galerkin? Same thing. Now, actually, it also matches the exact solution, just to let you know. It matches the exact solution. Let's take ODE. Let's take this functional. And I want to minimize that functional. Let's do it just to see what happens. Let's minimize this functional. So I'll minimize this functional. It's not even a total potential energy. It's not even that. It's just a functional. So I'll minimize that. Same step. Make U plus epsilon V. So substitute that in there. So we plug that in. Expand it out. You expand it out very nicely here. All of it expanded. Now take the derivative of this expression with respect to epsilon. And you can see this does not depend on epsilon, so that goes away. This has epsilon, so it's 2u prime v prime. That's that term. And so forth. You can go and check that I did it correctly. And then we set this epsilon equal to 0. I get this equation here at the bottom. U prime v prime plus uv plus v dx equals 0. This is what I get. All right. Why I'm giving this random example, right? Well, because last week, by the way, this example, if I multiply by -1 just for fun, I get the 1 here at the top. Last week, I gave you this governing equation, and we developed the weak form. I multiplied this by v. So I formed the residual, bring this to the other side, form the residual, make that orthogonal to the wave function, integrate it from 0 to 1, weaken the continuity requirements, and I get the weak form. And you can see here, if I impose the boundary conditions, which are the essential boundary conditions here, this goes away, like last week. I don't want to repeat what I did last week. And if I implicitly satisfy this natural boundary condition, I get that. Do you see a similarity between this and that? This one I obtained by minimizing the functional I gave you. This one I got from the weak form starting from the strong form. Well, so what does that mean? That functional is a function that corresponds to this problem. Okay, so I can use that functional to actually solve this problem and actually find the approximate solution to the problem. So then I can go ahead and plug in the approximation function. I won't discuss again how I got this because that was discussed in the weak form Galerkin example. I plugged that in into the functional I came up with, which was this one here, the original one here. That's the one I came up with. And I plug it in, this approximate solution. I didn't do all the operations because I have Mathematica. So I take the derivative of f with respect to C1, derivative of f with respect to C2, two equations, two unknowns. And then Mathematica gives me the answer. And guess what? The weak form Galerkin gives me the same answer as Rayleigh-Ritz. Matches, or doesn't match exactly, but is very close to the exact solution, within 0.5%. Really, really close. Are you seeing the connection? How weak form Galerkin is related to approximating the solution to a partial differential equation? Are you seeing the connection that if I have a functional, then when it's minimized, also gives me the weak form, which is connected to the strong form? And then me plug it in an approximation function into the total potential energy or functional, minimizing that basically gives me an approximate solution to the ordinary differential equation. Yeah? Okay, let's do two more examples. Simple examples. This one is one-dimensional bar, and we need to find the form of U. Okay, the form of U is very simple to find because we know that at x equals 0 is fixed, and that's the only essential boundary condition. So C sub 0 goes to 0, and the only terms I have are these guys. So U tilde is C1x plus C2x squared. That is the form that we're going to use for the approximate solution. If you want to look at the total potential energy of that bar, that's basically, I gave you the formula earlier. It's the same formula for a 1D elastic bar. So that's the formula. Here, in this case, the modulus varies. The modulus varies as a function of length. So you can plug it in here very nicely. So that's right there. This is actually very neat. And then I can plug in my approximation function in here for U tilde, and remember C sub 0 is 0. I plug it in. Again, let Mathematica do the homework or the work, but take the derivative of pi with respect to C1, derivative of pi with respect to C2. We'll correct that. And then we did the algebra here for you in case you don't trust Mathematica. Okay? And at the end, we have a 2x2 matrix, C1 and C2, and you can get C1 and C2. And then this gives you the deflection along the length of the beam. If I know the deflection along the length of the beam, I know the strain. If I know the strain, I know the stress. And that's what's shown here. If I know the displacements, I know the strains. If I know the strains, I know the stress along the length of the beam. Elastic bar, I'm sorry. Second example, in this example, which we covered this example, fixed conditions. So we covered that. So I don't want to show exactly how we come up with the form because we did it a couple of times now. But again, same concept. I have the total potential energy again. And then in this case, I only have one coefficient I'm going to use. And then derivative of pi with respect to C1 equals to 0. This is only one equation. I have only one coefficient. I didn't do two coefficients, 3, 4, 5, and so forth. So the more coefficients I add to this problem, the closer I will get to the exact solution. So the idea is you can refine, and let's keep that word in mind for later, but we can refine the solution by adding terms to the approximation solution. For the problems I'm giving you, I'm only asking you to do two unknown coefficients. You know, if I do 3, then you have to do is a significant amount of work, right? All I want to teach you is a concept so that we can keep moving forward here, okay? Finally, in summary, this is my last slide, the minimization of the total potential energy, in this case, that's a functional because it depends on function, is basically the weak form. We showed you that minimizing the total potential energy or minimizing the function gives you a weak form that corresponds to a strong form. And that substituting the approximation solution to the functional or the total potential energy in our physical examples, the minimizing the functional relative to those unknown coefficients basically give us the approximate solution to the partial differential equation. They're connected. Minimizing the total potential energy gives you the weak form. If I start from the strong form and I weaken the continuity requirements, I get the weak form. They're connected through the weak form. Okay? The Rayleigh-Ritz requires a functional. So that's one disadvantage of Rayleigh-Ritz. You have to have a functional in hand. You also have to show that that functional corresponds to the partial differential equation you're interested in. In the two examples I gave you, we were able to prove that, right? In the homework problem I gave you, you're going to prove that for me, right? You're going to show me, hey, this corresponds to the governing equation of the problem. But the Rayleigh-Ritz, requires a functional. That's the disadvantage. The advantage of weak form regularity, I can just start with the partial differential equation or ordinary differential equation. I can give it to you. I don't need to even know about the physics of the problem. I can start from there, the strong form. I create the weak form from there, and then approximate solution to the problem by creating a weighted residual. Okay. And so with that, that is the conclusion of today's lecture. And then please come forward. We have about a couple of minutes here to take any questions. Okay? Any questions? Any thoughts? Okay, I'm going to go off here.